So our next talk will be delivered by Felix Held, who just told me that memory is actually not a trivial problem. I didn't know that before. So let's give it up for Felix Held.
Hello and welcome to my talk about memory. First, what the talk will be about and what it won't be about. It won't be about the physical interface or the initial memory training. It's more a very brief and high-level overview about a rather broad topic. And the main question is the challenges how to scale the memory subsystem, because the processing power scales quite well. But in memory, we have we face some issues there. And to squeeze it all into 30 minutes, I had to omit a lot of details, but yeah. Basically, the challenges in the memory subsystem are mostly the throughput and the latency, and also the physical memory interfaces, but that won't be part of the talk. Basically, throughput is relatively easy to increase. Either you can add more data lanes on the high bandwidth memory, the number of data lanes was massively increased to, I think, 1024 data lanes. The other possibility is to increase the symbol rate per lane. That's done in for the hybrid memory cube, or also for the IBM Power 8 and 9 systems with the external memory buffers. Basically, they get, I think, 4 times the throughput when using the external memory buffer and speaking some very fast protocol over differential lanes compared to the normal DDR3 or DDR4 interface. And it also doesn't add that much delay. Yeah, another option would be to submit multiple bits per symbol, but that's currently not done on DRAM. Yeah. The other problem, and the way harder problem, is latency. That can't, or basically you have to fight physics there. There are basically 2 main problems there. One is the speed of light in a medium, which isn't a vacuum. So basically how fast the data can go through the interconnect in the chip. And it's about half of the speed of light. And the other problem is basically the interconnect has a certain resistance. And the MOSFETs, the switching transistors there, and the capacitors where the ones and zeros are stored are capacitors. So basically you have a low-pass filter, and the edge frequency of the low-pass filter also doesn't really decrease with die shrinks, because sure, the capacitors become smaller, but also the interconnect becomes smaller, so the resistance of the interconnect increases. So yeah, it doesn't get that much better. So yeah, basically the data throughput can be easily increased, but the time to get a certain data word to the processor stays about the same. I think over the DDR 2, 3, and 4 memory generations, there was only a very slight improvement there, but the throughput became much higher. So let's look at the DDR RAM chips. Basically, those are optimized for capacity and cost. So a rather big amount of memory, but in the design they had to cut some corners to bring the cost lower. And basically the architecture, you have command bus, send commands to the device. You have a bidirectional data bus, Basically, you have the same 64 or 72 bits for one memory DIMM to read and write data. The chips have multiple banks and the memory is organized in rows and columns. Some nice diagram there. It's taken from a DDR3 memory datasheet. Basically, you have there the command and address input lines. Here you have the data bus and the data strobe signals. Basically, the control interface, you have a clock, and on each, I think, rising clock edge, you can send it in your command, like read or write. I'll get to that in a bit. And you have a data bus. It's for every 8 bits in the data bus, you have one differential strobe line. And basically, that line tells when to sample the data on the data bus, or when the data is valid and stable. And yeah, basically, we have 8 banks of memory. And in one bank, it's an array with different rows and different columns. And when you access the RAM, basically you tell first which row you want to access. Then the row gets loaded into the sense amplifiers. And then you can select which of those columns you want to access. And that's then put into the buffers of the read and write interface, or the data interface. Yeah. The data interface, it's at a double data rate. Basically, it uses both edges of the strobe signal to transmit data. But the command interface, it only uses one edge of the clock. So you get so basically the data rate is at least double of the command rate. But when you have a lot of memory in the system, and basically on a memory module, the different, or on a single rank memory module, the different chips share the command bus, but have separate data buses. So the load on the address and control lines is much higher than the load on the data lines. And there you can also select the half command rate. So only a command is issued with for or every 2 clocks on the command bus. That helps a bit. Other thing that's done there is for the registered memory. To support more memory, basically a small chip is put in front of the command bus, which is more or less just redriver for the signals that has, or basically it reduces the bus load when having multiple memory modules. Yeah, but having or being able to send less commands than you can transfer data isn't a big problem, because in DRAM the data is usually transferred in bursts. So go back to this slide. Basically, from when you select a column, you get 64 bits of data. You have a FIFO or multiplexer there, and yeah, 8 bit lines to the outside, and you have a burst length, typically a burst length of 8. So you send one command, and then send 8 data words, or get 8 data words back. That's I'll show later why that makes sense. Yeah. The memory access, basically inside the memory, you have a sort of state machine. It starts in the when a bank is in the idle mode. Then you send a command to open a row in a bank, and that takes a certain time before you can submit read or write requests. That's the TRCD delay. It's for DDR3 and 4. It's in memory clocks and not in absolute units. So basically, when you look at data sheet from DDR2 memory and look at a data sheet of DDR4 memory, it seems that the latency got worse, but it didn't get worse because the frequency increased, and with that also the numbers increased. But the absolute value didn't change that much. Yeah, when you have then activated a row, basically load that into the read amplifiers. Then you can access the columns inside the row. Can send there either a read request or write request. And it takes the read request takes the certain time CL until the data appears on the data bus. So there's all those commands have certain latency. And also for the write, you have the CWL delay until after you send it the write command when it starts reading data from the data bus. And yeah, the read and write commands, you can specify that you either want to do another read or write command in the same row, and then it keeps the row open. Or you can say that it should automatically close the row, or you can also explicitly say that you want to close the row. That's the pre-charge. And yeah, it takes then the TRP delay until the next activate command can be sent on that bank. And that's also why we have multiple banks there. For DDR3, it's 8 banks. So with interleaving those accesses, you can sort of mask those delays. Yeah. Then the next element is the memory controller. Its main job is just to take the load and store requests from the different processing units on the chip or in the system. For example, also PCI Express devices that do DMA via bus mastering. Also very important that it has to take care that there won't be collisions on the data bus, because the memory data bus is bidirectional, and when you mess up the timing between those reads and writes, it could happen that both the memory chip outputs some data on the bus and the memory controller outputs some data on the bus and get in a bus fight, and that's not good. So yeah, it has to schedule those commands properly. That never happens. It also has to take care of the periodic RAM refresh, because it's dynamic RAM. It only holds the ones and zeros in the capacitor, and over time those electrons go away from there, and so you have to periodically refresh that. Yeah, and also it has to make sure that the RAM stays in its thermal budget, because when you access the RAM at full possible speed, after some times it will heat a lot, and then the chance of bit flips increase, and possibly also destruction of the chip. But I haven't seen memory being destroyed by accessing it too much, but yeah, you should make sure that that doesn't happen. it's also for scaling memory accesses from the different units and at the different places in the main memory. Because if you don't schedule that properly, you don't really use the available bandwidth efficiently. And yeah, we want to try to use the memory bandwidth quite efficiently. And the other problem is it has to solve it's to map the physical addresses to memory locations. And basically for the memory locations we have different parameters. That's the channel. So if you have multiple channels on a processor, then the rank. One memory module can be or can have one or multiple sets of memory chips on it. And when you put more than one memory module on one channel, it also increases the number of memory ranks. I'll go into that later a bit. Then the bank and the row addresses. So yeah, let's look a bit more into that. So the channels are typically used or mapped interleaved. So when you do a sequential read on memory on a continuous range of memory, you can use the sum of the bandwidth of both channels. And yeah, sure, you use both memory channels, then the power, then you basically double the dynamic power consumption. And yeah, but you mostly have more than just one access, so also in different locations, but usually having the memory interleaved increases the performance. Then we have the different ranks. Those share the command and data bus. Basically, it's a memory module with 2 ranks, or a DIMM with 2 ranks is about the same as 2 memory modules with 1 rank each. It's, yeah, there's only some one enable line and one line for the termination resistors to avoid reflections on the data lines. But yeah, otherwise they are basically in parallel. And yeah, the internal state of the memory, it's basically, those are separate memory chips. And yeah, it's mostly used for increasing the total memory capacity on a system. Yeah. Then we have the banks, basically the 8 different sets of the memory arrays. And those are typically used or mapped interleaved. So basically when you finish reading one row, you want to read the next row from a different bank, because then you can open that row basically before closing the row that you're currently reading. And then you basically can mask the latency, because when the one row is closed, the other is already opened, and then you can just continue reading or writing the memory. And yeah, having more banks open also increases the power consumption, but gives more throughput. And yeah, then are the row addresses, so the rows in the memory array. And yeah, as I already told, those are often not mapped continuously, and instead the banks are interleaved. And finally, we have the addresses in the columns. And typically the memory addresses or the lower bits of the memory address get directly mapped to the offset inside the column. Because it's quite common that you just read multiple, or that you read a continuous segment of memory. And also the latency of accessing different columns in one row, it's quite low, because you don't have to close the row and reopen another row. Yeah. Now, next element in the system are the caches. Basically, they help solving at least part of the latency problems. Because, yeah, if you have a larger memory, the latency increases. Basically, all the lines in the memory get longer, and also for higher capacity, you rather use DRAM, and for low capacity, you can use the faster SRAM, which takes more space on the chip, though. But, yeah, so smaller memory, or you can implement a memory with lower latency only if you use SRAM and only have a certain and decrease basically the area. But yeah, SRAM takes about, I think, 6 times more space than DRAM. So yeah, that's basically putting a gigabyte of SRAM on a computer, basically can't afford that, or you try not to use that. I think there are rather big SRAM chips, like 64 megabytes or so, used, for example, used in routers for the route tables, or part of the route tables. But those memories get really, really expensive. And yeah, what the cache, or basically what the cache uses, that memory accesses are often either close together, either in time or in the memory space. So you try to keep a small amount of memory that's currently used in a small memory region, and you also try to keep that more or less transparent. So what's used on some ARM microcontrollers is that you have the tightly coupled memory. That's an SRAM that sits rather near to the processor core. But those are that's only mapped in a certain location and doesn't accelerate the rest of the memory, and you have to explicitly use that memory location, and so you have to adapt the software, and yeah, for some special cases it makes sense, but for the general case it's not that feasible. Yeah, for the caches, you have a certain amount of memory. Basically, you have it's next slide. Yeah, the smallest amount of the memory that can be put in the cache is one cache line. On x86, it's typically 64 bytes. But yeah, where the number is coming from, basically, the DDR DIMMs have 64 usable data bits, or 72 when using ECC error correction, but effectively 64 data bits. And the burst size is 8. You multiply that, you get the 64 bytes. So yeah, basically the caches and the memory that size fits together. And yeah, the other address bits, or the lower address bits, address the offset in the offset in the cache line, and the higher address bits they get hashed, but it's not a cryptographical hash. It's more like some address bits get XORed together, and then you have. Then this hash is used to see in which position in that cache line can be put. So basically, when you have a fully associative, how to pronounce that, or associative cache, then you can put every cache line in every position in the cache. But you need a lot of hardware to implement that. And so basically, I think in modern processors you have an associativity of 16 or 24, basically, when that hash has a certain value, you have then 16 or 24 cache lines where you could put it there. And for each cache line, also the higher part of the address that's cached there is put in the tag memory. And so basically, when the processor does memory access, the cache controller takes the higher bytes or the higher bits of the address, uses the hash function on that, and then looks if in the 16 or 24 places where that could be, if the higher bits of the address match the tag, and if so, the data is cached and can be accessed from the cache. If not, then it has to be fetched from either the next higher cache level or from the main memory. And you have only 16 or 24 places where you can put a certain cache line. And so you need a replacement strategy. There are basically two main strategies, or three. Forgot the random one. Basically, you see the last of those. The oldest of those 16 or 24 places, and then replace that. That's the least recently used. Or you have the least frequently used strategy, where you see how often a value or a cache line was accessed, and the cache line that was accessed least often, that gets replaced. There's also the random replacement strategy, but yeah, those two strategies are better. Yeah. Then in modern computer architectures, you usually have multiple levels of caches, because if the memory is bigger, the memory gets slower. And so basically you use a combination of smaller and faster memory nearer to the processing elements, and bigger and slower memory than more far away from the processing elements and nearer to the DRAM. And there's also if the cache is inclusive, the next higher cache levels always contain the data that's in the lower cache levels, and also I think that's used on most systems. And there's also the exclusive strategy where a cache line, when it gets moved from a higher level cache to a lower level cache, it's basically moved there and not kept in the higher level cache. And also you have different write strategies. Either you can write through. Basically, when the processor writes, the write will be propagated from one cache level to another and then to the main memory. Good thing there is that you need less state tracking, but bad thing is that you need much more write bandwidth. Other strategy is the write back strategy. There, basically, you only write the cache contents back to the next higher level when it gets evicted from the local cache, or when when it gets invalidated, it's invalidated in both. And but downside from that is that you need to track or to keep track of more internal state. It's you have to basically you have to find a compromise there. Then the next thing is when the processor loads data from the main memory, the latency is not very predictable. If it's the data is in the level 1 cache, you get that within maybe 10 to 20 cycles. And basically the next levels of caches or main memory, that's basically a factor 10 in latency. So the latency between those accesses can vary very much. But you don't want when you access or you read some data, you don't want that the pipeline stalls. So memory latency has an impact on how the microarchitectures of the processor are built. Because for the single thread case, basically you have to do out-of-order execution. So basically you reorder the instructions to run when you wait for that you get the data from a read, that you just process some other instructions that don't depend on that data. And for that load, it's basically sent to the caching subsystem. And then after some time, you get the data back in the load buffer and can then work on the data. And it's basically the out-of-order execution is needed there to keep the processor busy, because if the processor is just waiting for data, it doesn't do anything useful. And the other thing you can do about that, if you need mainly multi-thread performance, then you can, or what Intel did is introducing the hyperthreading. If the main problem in the program is waiting for data getting data from the memory, that's quite helpful. But if it's computation constrained, the hyperthreading doesn't help that much. And also, you want that when you access data, that the data is already in the cache. So there's the cache prefetching. And basically for the instructions, the branch prediction is used to, the processor thinks, well, probably that instructions will be executed. And then the prefetcher makes sure or tries that those instructions are already in the instruction cache. Same for the data reads. The processor tries a bit to detect the access patterns, and there are also some cache hinting instructions. Basically, we can tell the processor, well, don't cache that stuff to invalidate a lot of cache lines, or, well, I need that memory, please load it, already load it into the cache. Another problem with cache is the cache coherency. So if you have multiple processors in the design, you have to make sure that when multiple processors have the data from the same address in their cache, and one writes to that the cache contents of all the other processors have to be invalidated, so that the other processors don't work on invalid data. And there's also different stuff that can be done, but I think I should skip that. And the processor instruction set specification also gives you some guarantees which accesses can't be reordered and which accesses can be reordered, because sometimes reordering some accesses can also improve the throughput, but that's something the programmer have to be aware of, because when building synchronization primitives, then you really have to know which accesses can be reordered, and if some accesses can be reordered, we really need it to be that they must be reordered. You can insert a memory barrier, but that memory barrier is really expensive because it flushes state. So, thank you for your attention.
Thank you very much. Have a round of applause for Felix Held. And we have quite a lot of time for questions, so if you have any.
Just a very quick question. Given a cache miss, what's the optimum alignment for DDR memory? The optimum data alignment. So given a cache miss, when you have to access DDR, if you want to allocate some memory, what's the optimum alignment for that memory, for latency? What's the optimum alignment? So for memory allocation for DDR,
the memory
I usually align on cache size, cache line size, but
yeah, the alignment should be those 64 bytes. It's the cache line size, but also basically the amount of data you get in one data burst from the RAM or can push to the RAM.
Any more questions? Okay, first, then.
Hey, so what we heard here was a quite detailed overview on how a memory works, I think, on a quite theoretical level, but fair enough. I'm missing a bit from your statement or from the title about the hard problem, right? So what is the problem statement?
Latency.
The latency,
Yeah.
actually. Okay, I was a few minutes late, so maybe I missed that at the beginning.
Yeah.
So that was what your focus on, that we
Yep.
have latency issues, okay.
Basically, you can increase the data throughput, but you can't really decrease the latency. And basically what you have to do in the whole computer architecture to address that problem.
So quite a few questions. So first of all, why does the command line, so the command clock, only use one edge of the clock and not both, like the data line does?
Well, on the command bus, you need much less throughput.
Again, please.
You need less throughput on the command interface.
Okay, so you don't have to use the second clock.
Yeah, and the other reason is basically on one memory chip, if the interface of the whole DIMM is 64-bit, and typically the memory chips have a data interface of 8-bit. The data interfaces are wired to the data bits, but the command interface, all chips are in parallel on that interface. So you have a much more load on that interface, and so you can't use that high clock.
Oh, okay. Next question. So the main problem for the future concerning memory is the charge and discharge time of the capacitor to reduce the latency, right? Is this the main problem when it comes to latency, or?
Yeah, one problem is the charging and discharging of the capacitor, and the propagation delay on the die.
Online. Oh, okay. And you mentioned.
And also on the PCB, of course.
Okay. And you also mentioned load buffers just a few minutes before. What exactly are those?
For the load-reduced DIMMs, basically you have one chip on a module where all the command lines or the command interface gets connected to, and that chip distributes that information to all the command interfaces of all chips on the DIMM. And basically, with that, you can reduce the load on the command bus when having multiple DIMMs in the system. So it's assuming you have a dual rank module with 8-bit chips, then it's then with that command bus buffer, then you decrease the bus load of the on the command interface to 16th, and so you can use much more memory. And there's also the fully buffered memories. They also have buffer on the data lines, but you only need that when you put really huge amounts of memory in server.
Okay, are there any more questions? Okay.
When looking on the hash algorithms of the, I think it was Intel chips, I found that in the past they had very simple algorithms,
Yep.
but they moved to more or less specific algorithms. Do you know the background of this? Is it performance reasons or?
It's basically with that you try to avoid that near memory locations get mapped to the same hash value, and then have to share the cache lines.
Okay, thanks.
And I think some people reverse engineered that for, I think, the Sandy Bridge and Ivy Bridge processors. And also via timing. Yeah, they usually change from generation to generation.
Are there any more questions? Okay, then give a round of applause, Felix Held. Thank you very much.